To look at mechanics geometrically, we often use phase space, a space of two s dimensions whose axes are the s generalized coordinates and the s momenta. Each point of it corresponds to one definite state of the system. As the system moves, the point representing it traces out a curve called the phase path. The product of all the differentials may be regarded as an element of volume in this space. Consider the integral of that element over some region, which is simply the volume of the region. What we shall show is that this integral is invariant under canonical transformations. Changing variables in a multiple integral brings in the Jacobian of the transformation. So what has to be proved is that the Jacobian of every canonical transformation is equal to 1. Jacobians have a useful property. They can be handled somewhat like fractions. Dividing numerator and denominator by the old coordinates together with the new momenta reduces it to a ratio of two determinants of order s. Writing the transformation through the generating function of the old coordinates and the new momenta, the element of the determinant in the numerator is its second derivative by an old coordinate and a new momentum. The element of the determinant in the denominator is that same second derivative with the two indices interchanged. The determinants therefore differ only by an interchange of rows and columns, so they are equal and the ratio is 1. Now the key step. At the end of the last lesson, we saw that the evolution of the system in time is itself a series of canonical transformations, whose generating function is minus the action. So if every point of a region moves according to the equations of motion, the region moves too, and it may be stretched, sheared and drawn out into very fine filaments, yet its volume never changes. This is Liouville's theorem. In other words, the phase flow behaves like an incompressible fluid. The same argument shows that integrals over manifolds of 2, 4 and more dimensions are invariant as well, and these are the Poincare integral invariants.